Scientists detect invisible electric field around Earth for the first time. An invisible weak energy field wrapped around our planet Earth has finally been detected and measured. It's called the ambipolar field, an electric field first hypothesized more than 60 years ago, and its discovery will change the way we study and understand the behavior and evolution of our beautiful, ever-changing world. And I bet you that the ancients knew about these fields. Hence their power plants and their knowledge of ley lines and where to build their temples and pyramids. Now, going back to this, any planet with an atmosphere should have an ambipolar field, says astronomer Glyn Collinson of NASA's Goddard Space Flight Center. Now that we finally measured it, we can begin learning how it shaped our planet as well as others over time. Earth is not just a blob of dirt sitting inert in space. It's surrounded by all sorts of fields. There's the gravity field. We don't know a lot about gravity, especially considering how ubiquitous it is, but without gravity we would not have a planet. Gravity also helps keep the atmosphere snug against the surface. There's also the magnetic field, which is generated by the rotating conducting material in Earth's interior, converting kinetic energy into the magnetic field that spins out into space. This protects our planet from the effects of the solar wind and radiation, and also helps to keep the atmosphere from blowing away. In 1968, scientists described a phenomenon that we could not have noticed until the space age. Spacecraft flying over Earth's poles detected a supersonic wind of particles escaping from Earth's atmosphere. The best explanation for this was a third electric energy field. It's called the ambipolar field, and it's an agent of chaos. It counters gravity and it strips particles off into space, Collison explains. But we've never been able to measure this before because we have not had the technology. So we built the Endurance rocket ship to go in looking for this great invisible force. And here's how the ambipolar field was expected to work. Starting at an altitude of around 250 kilometers, that's 155 miles, in a layer of the atmosphere called the ionosphere, extreme ultraviolet solar radiation ionizes atmospheric atoms, breaking off negatively charged electrons and turning the atom into positively charged ion. The lighter electrons will try to fly off into space while the heavier ions try to sink towards the ground, but the plasma environment will try to maintain charge neutrality, which results in the emergence of electric field between the electrons and the ions to tether them together. This is called the ambipolar field because it works in both directions, with the ions supplying a downward pull and the electrons an upward one. The result is that the atmosphere is puffed up. The increased altitude allows some ions to escape into space, which is what we see in the polar wind. This ambipolar field would be incredibly weak, which is why Conlison and his team designed instruments to detect it. The Endurance mission carrying this experiment was launched May 2022, reaching an altitude of 768.3 kilometers, that's 477 some odd miles, before falling back to Earth with its precious hard-won data. And it succeeded. It measured a change in electric potential of just 0.55 volts, but that was all that was needed. A half a volt is almost nothing. It's only about as strong as a watch battery, Collins had said, but that's just the right amount to explain the polar wind. That amount of charge is enough to tug on hydrogen ions with 10.6 times the strength of gravity, launching them to space at the supersonic speeds measured over Earth's poles. Oxygen ions, which are heavier than hydrogen ions, are also lofted higher, increasing the density of the ionosphere at high altitudes by 271% compared to what its density would be without the ambipolar field. What's even more exciting is that this is just the first step. We don't know the broader implications of the ambipolar field, how long it has been there, what it does, and how it has helped shape the evolution of our planet and its atmosphere, and possibly even the life on its surface. This field is a fundamental part of the way Earth works, Collinson said, and now we finally measured it and we can actually start to ask some of these bigger and exciting questions. The research was published in Nature magazine, so this is amazing, isn't it? This is by Michelle Starr on Science Alert. Please leave your comments and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.